We've learned that autonomous differential equations are differential equations where the independent variable, usually t or maybe x, does not show up explicitly. So only the dependent variable. The derivative only depends on the dependent variable. So in other words, you have dy dt equals, and then what's over here is just stuff including y, no t at all. Right, so that's called an autonomous differential equation. In this video, we're going to talk about something special we can do with autonomous differential equations. Okay, now, first of all, let me just go over what we already can do with autonomous differential equations. First of all, the place where we've already encountered autonomous differential equations is when we were talking about separable DEs. Autonomous is always separable. So you might be able to get a formula for a solution using separation of variables. That may or may not work. Of course, if that works, that's great, but of course, you may run into some antiderivatives along the way that prevent you from finishing it off. But that's always, of course, a great thing to try. Now, you can always create a slope field. Of course, that's true for all differential equations, all first-order differential equations anyway. You can always create a slope field, so that's no different for autonomous ones. And you can always do a numerical solution using Euler's method. Again, that's true for all differential equations, not just autonomous. And so we have the analytic, the qualitative, and the numerical approaches all represented here. What we're going to talk about now is a new qualitative approach that only works for autonomous differential equations, and that's called phase lines. Let's look at an example. So we have dy dt equals 0.3 y times the quantity 1 minus y over 5. So this is actually a logistic differential equation. This is one of the models we've seen before. It is autonomous, right? Only y shows up on the right. There's no explicit dependence with t. Okay. Now you could solve this with separation of variables with a little bit of effort. It will be a tough but doable antiderivative, and you could solve it through. But let's not take that route, okay? Well, first of all, we're doing qualitative. Now we already know that we can do slope fields, and here you see a picture of the slope field that goes with this differential equation. Now, for autonomous differential equations, and we discussed this, when it only depends on y, you're going to get the same slopes across any horizontal line, right? Because across a horizontal line, for example, this one, your y is 4 the whole time. What's changing is t as you go from left to right, but t doesn't matter up here. So this equation is always going to give you the same slope. So you basically have each column is just repeated each time, right? Each column has all the information, and you're just repeating that column after column after column, right? Because horizontal kind of doesn't matter here in terms of, at least when you're worried about the slope. So it seems like kind of a waste of effort to just repeat that same column of slopes over and over and over again. And so that's what a phase line is. It's kind of a simplification of this. But yeah, it would only work for autonomous ones where we have this situation where it's the same slope going from left to right. So instead of doing a full slope field, we just do a simple single line. And this is how it works. First, decide which values of y would give you a slope of 0. And so that usually amounts to a little algebra problem, right? Equals 0. We want to put a 0 in for dy dt. I'll put it over on the other side. And in this case, it's easy because we're factored already, and we can see that y would be 0, or y would be, you can see 5 would work. So 0 and 5 are the two places where the slope is 0. Now those are called equilibrium, and we've run into this word already, equilibrium solutions. And when we're talking about phase lines, we actually just call them equilibrium points. And on our phase line, we mark off little dots right at those points. So there's 0 and there's 5. And I'm trying to make it sort of horizontally match up with my slope field over here. On the slope field, of course, it's right where our slopes are going straight across horizontally, like that. Yeah, so they're the constant solutions. Y equals 0. If you start at 0, you will stay at 0. If you start at 5, you will stay at 5. So we mark those off on our phase line. Okay. Now, here's the thing. That divides our phase line into 3 sections, up here, in the middle, and down here. Now, in each of those, let me start over. In each of those sections, the slopes are either positive or they're negative, but they can't be both. So in other words, this section here consists of only positive slopes or only negative slopes. It can't have both, because if there was positive slope and negative slope, then there would be 0 in between, at least assuming that this is a nice continuous formula, which it almost always is. So since we've already separated out the places where it's 0, the remaining segments must be all of one or the other, all positive or all negative. Now we already can see from the slope field that was done for us that it's going to be negative, but if we didn't have this picture already, what you would do is you would just pick any point you want, like 6 or 10 or something easy, and put it in your differential equation. So let's say 6, so we would get 0.3 times 6 times 1 minus 6 over 5. And unlike the slope field, it's not so much the number, but it's the plus or minusness of it, right? It's the sign. So this is a positive number, this is a positive number, and we can see that that would actually be a negative. So the end result would be negative. So we know that in this area the slopes would be negative, which means the function would be going down. And what we're going to do is we're going to indicate that with an arrow pointing downward. Okay, and that's just, that arrow represents this whole segment from 5 on up. Now we do the same with the other 2 segments, 0 to 5. Again, it's got to be all positive slopes or all negative slopes. So we figure out which one it is. I know the slope field's already telling it to us, but like we would, for example, pick a number like 1, and we would put that in here, and we get 0.3 times 1 times 1 minus 1/5. 1 minus 1/5 is a positive number, and of course the rest would be positive. So it's all positive in here, positive slopes, which means our function would be increasing. So we make an upward arrow. And then finally, for the third segment, pick a number like -1. If you put it in here, now the y right here would be negative. 1 minus a negative would be positive. So we'd have 0.3 times a negative times a positive. That would be negative. So we put a downward arrow. So that's our phase line. Now, and the idea is this phase line, maybe roughly, but nonetheless, tells us the behavior of our function. We know, again, the equilibrium points are always our starting points. Anything that starts at 5 would stay at 5. Anything that starts at 0 would stay at 0. Anything that starts in the middle would have to go up. But we combine that with the fact we've talked about that solutions don't cross, right? They can't cross. So this thing, although it's going up, is going to have to level off and kind of asymptotically approach 5. Anything that starts up here, we know it has to go down. But again, it can't go down past 5, so it asymptotically approaches 5. Now, anything that starts down here, this is slightly different. It goes down, but there's nothing to prevent it from just going down forever. Okay, so these are the 3 behaviors. It can go down and level off at 5. It can go up and level off at 5, or it can just go down without leveling off at all, just down to negative infinity. Those are the 3 behaviors, and it depends on where you start. And this phase line has all that information in it. Now we've lost a little bit of information. I don't know exactly how fast this curve goes down to 5. I don't know if it goes down really fast or it takes its time. I don't know if this one kind of goes up really fast and then levels off, or again takes its time. It could be any one of these. Because we're just putting an arrow here, we're losing a little bit of information about how it's moving in that way. The slope field has that for us because the slopes tell us exactly how it's supposed to go. So yeah, but we're we're giving up some information, but the benefit is it's a very concise way of saying something important, which is just, where it goes up, where it goes down, and the ultimate behavior. Let's try another one. dy dt equals y squared minus y minus 6. Okay, so it's autonomous. It's actually, we don't have a slope field. We could get a slope field, of course, and we could do all those other things. We could do Euler's method. We could attempt to solve it using separation of variables. But let's try this phase line approach. So I'm going to draw a phase line. I get my equilibrium points. So I set this equal to 0. I just want to see what y's would give derivatives of 0. So it's a quadratic, so of course my first approach is to try to factor it, and this one does. All right, I think we get -3 and plus 2. So y would be either -3 or positive 3 and -2. So, okay, if I put let me put a scale on this. Let's go 0, 1, 2, 3, 4, -1, -2, -3. Okay, so at +3, I put a dot. At -2, I put a dot. All right. Now, again, 3 segments. Whenever you have 2 equilibrium points, you're going to have 3 segments that your phase line gets broken up into. Let's pick one up from up here. Let's try like 4. If we put in 4, I can either put it into the original, or of course I can put it in the factored version. The factored version might be simpler in this case. 4 minus 3 is 1. 4 plus 2 is 6. 1 times 6. It's positive. So I have an upward direction in that area. Okay, 0 is always an easy number to plug in. I think I'll just plug that into the original, and I can see I get -6. So this one is downward. And then -3 is another possibility. I could plug it in here, or maybe the factored version. If I plug in -3, that will be negative, and that will be negative, so that would actually be positive. Okay, so my phase line is done, but again, just to spell out what it's actually telling us. Solutions that start at 3 stay at 3. Solutions that start at -2 stay at -2. Those are just going to be horizontal constant function solutions. Anything that starts above 3 is just going to go up. Anything that starts between 3 and -2 is going to have to go down. But because -2 is below it, it's going to have to level off, so it asymptotically approaches -2. And anything that starts below -2 is supposed to go up, but again, it's going to have to level off because it can't pass -2. So these are the possible behaviors. Based on where you start, you have different things that could happen. Let's try another one. dx dt equals e to the x quantity x cubed minus 2x. Now x is our dependent variable, just changing it from y just to switch things up. I know x can sometimes be the independent variable, but not here. X is dependent. We still have t as the independent variable. So this is autonomous. Okay, so we want to do a phase line. We first find the equilibrium points. We set this equal to 0. I'm already going to factor out an x. I see that I can do that. E to the x times x squared minus 2 equals 0. And in fact, that can further be broken down into x plus root 2, x minus root 2, difference of squares. Okay, so I can see that x could be 0, or negative root 2, or positive root 2. By the way, the e to the x factor can never be 0, right? E to the x never equals 0. All right, so let's put a dot at 0. Root 2 is somewhere between 1 and 2, so if I just mark off some points here, root 2 is going to be somewhere in here, and negative root 2 is going to be somewhere in here. And I'll label them. Okay, so we have 3 equilibrium points, which means 4 sections to test for positive or negative slope. All right, so if I pick a number like 2, I can see I get 8 minus 4. E to the x, by the way, is always positive, so that's not going to play a role in the sign. So yeah, positive. So I have an upward arrow right here. All right, a number like 1 seems nice and simple for this upper middle section. 1 minus 2 is negative, so down. Let me use another color just so it comes out a little more. Okay, negative 1, I would have negative 1 plus 2, that'd be positive. And then finally, negative 2, that would give me a negative 8 plus 4, so a negative. All right, so there's our phase line. And once again, to really spell this out, it means constant solutions here, here, and here. Solutions here go up. Solutions that start in here go down and level off to 0. Solutions here go up and level off to 0. And solutions here go down. Okay. Now, one thing that happens a lot, and it's tempting to think it happens all the time, is that as you go from one segment to the next segment, it always switches. It doesn't. It has in these examples, but it doesn't have to. We could definitely have 2 up arrows in a row or 2 down arrows in a row. That is possible. So you do have to sort of check each one separately. Let me also say that you can have any number of equilibrium solutions. You could imagine that if we had a sine or a cosine over here, right, there are infinitely many places where that equals 0. So you would have infinitely many equilibrium points. And obviously you couldn't draw them all, but you could draw sort of a sampling of them and then do the in-between parts and see how that works out. So that you can do that with those kinds of problems as well. All right, a little bit of terminology that goes along with this. Our equilibrium solutions can be classified. You can see that, for example, in this example, let me take the 0 equilibrium solution. Oops. Now, if you start above 0 or below 0, either way, we see that from the phase line, we can see that those solutions sort of come back to 0. They converge to 0 over time. They asymptotically approach 0. So the word for that is that we say 0 is a sink. It's a sink. So the idea is if you start near 0, you kind of get pulled towards 0. It's like water going down a drain in a sink. It all gets pulled down to that point. So those are called sinks. On the other hand, square root of 2, if you start above square root of 2 or a little bit below square root of 2, you actually will end up going further away from square root of 2. Those equilibrium solutions are called sources. Okay, and the idea here is, even if you start at just a hair above square root of 2, right, just a tiny bit, still the phase line tells us that the differential equation is going to push you away eventually. Maybe you'll stay close for a while, but you'll get pushed away eventually. And the same on the other side. Right? So you have to be right on the nose square root of 2. You have to be exactly on square root of 2, or otherwise you will eventually go far away from it. So it's really touchy. It's sort of an unstable equilibrium, which is another word that is sometimes used. Unstable equilibrium. Sources are unstable equilibria. Sinks are stable. You have a little bit of leeway, right? If you could start a little bit away from 0, but you'll get pulled back to 0. So, you don't have to be as careful. It's that kind of an idea. Now, we didn't see this here, but if we had a phase line that had an up on both sides, or conversely a down on both sides. Okay, what do we call that? That's neither a source nor a sink. So we have the equilibrium, and if you start on one side, it goes up. If you start on the other side, it also goes up and comes to your equilibrium. So it's sort of stable on one side and unstable on the other side. So this is called a node. That's the name for it. So you see there are three types of equilibrium solutions, equilibrium points. You can be a source, a sink, or a node. Okay, so that'll wrap up this little topic. Just to summarize, phase lines are a nice, quick, easy way to get some qualitative information about solutions from. They only apply to autonomous differential equations, but they're really nice if you don't have technology nearby. It's very. This is the kind of thing that lends itself to doing it by hand. Of course, sometimes technology. There is software that can do this. But it's sort of unnecessary. It's not that much work to do it. So this is a sort of a nice by hand technique. In fact, our calculators, our Texas Instruments calculators, do not do phase lines. Of course, they do slope fields, so that supersedes it. A slope field includes all the information a phase line would, plus more. But phase lines are nice and succinct, concise way of saying how the solutions will behave.